Let us go back to our spin echo pulse sequence. This sequence can be illustrated schematically like this. 90-degree pulse, weight half of TE. 180-degree pulse, weight half of TE. Record signal. For certain different reasons, such a pulse sequence is repeated 2 or more times. The time to repeat a pulse sequence was TR, time to repeat. Time from the beginning of one 90-degree pulse to the next 90-degree pulse. So what we get is the following scheme. 90-degree pulse, half of TE. 180-degree pulse, half of TE, recording signal at TE. After TR, there follows another pulse cycle and signal measurement. 90-degree pulse, half of TE, 180-degree pulse, half of TE, recording signal at TE. By the way, what is a long TR or TE? To figure out how much signal you get from a certain tissue with certain parameters of a spin echo sequence, you actually have to do no more than combine its T1 and T2 curves. Here we have the T1 and T2 curves of a certain tissue. T1 represents the longitudinal relaxation, and T2 represents the transversal relaxation. Which parameter determined the amount of longitudinal magnetization? That was TR. To see how much longitudinal magnetization will be tilted 90 degrees to the side, and thus to figure out with how much transversal magnetization we start out with, we just look at the intensity of the longitudinal magnetization at the time TR. The longitudinal magnetization at this point, tilted in the transversal plane, is the starting point from which transversal magnetization decays. So, we just attach the T2 curve at this point. How much signal we get with a spin echo sequence to construct the image also depends on TE, the time that we wait after the 90-degree pulse. So, we now only have to look for the signal intensity at the time TE on the T2 curve. What image do we get when we choose a long TR and a short TE? Here are the T1 and T2 curves for two different tissues. As we heard earlier, with a very long TR, all tissues will have totally recovered their longitudinal magnetization. Differences in T1 of the tissues examined will not influence the signal, as enough time has passed by to allow even tissues with a long T1 to relax totally. So when we choose a long TR, as we just said, then differences in T1 do not really matter. When we also use a short TE, differences in signal intensity, due to differences in T2, have not had enough time to become pronounced yet. The signal that we get is thus neither T1 nor T2 weighted, but mainly influenced by differences in proton or spin density. The more protons, the more signal, if you look at it simply. And what happens when we use a long TR and a long TE? With a long TR, there are no prevailing differences in T1. With the long TE, however, differences in T2 become pronounced. Thus, the resulting image is T2 weighted. What if we use a shorter TR and a short TE? With a short TR, tissues have not recovered their longitudinal magnetization. Thus, differences in T1, which determines how fast longitudinal magnetization is regained, will show up in form of signal intensity differences. When TE is short, differences in T2 cannot really manifest themselves. So the resulting image is still T1 weighted. There is a lower limit for TE because it takes some time for the 180-degree pulse to be sent in and to properly take effect. What if we use a very short TR and a very long TE? This is only a theoretical question. Why? With a very short TR, there will only be very little longitudinal magnetization which is tilted. And with a long TE, we even allow the small amount of transversal magnetization resulting to disappear to a large extent. The resulting signal will be so small, of so little intensity, that it cannot be used to make a reasonable image. If you've not been concentrating for the last few minutes, you're probably thinking about giving up right now. How to remember this? Even if you don't understand all of it, which hopefully is not the case. Try looking at this illustration. What can you see? A man with short trousers. And considering the weather conditions, this makes only one person in the picture happy. This should remind you that a short TR, trousers, gives a T1 weighted image. Only one is happy. And what can you see in this illustration? The same couple is having tea. Now, having tea, which is usually served hot, always takes a long time. And in the illustration, the long T makes two people happy. This should remind you that a long TE gives a T2 weighted image. How can we tell from an image whether it is a T1 or T2 weighted image when imaging was done with a normal pulse sequence, not one of the fast sequences, which we'll hear about a little later? As a rule of thumb, if you see white fluid, for example, CSF or urine, you're dealing with a T2 weighted image. If the fluid is darker than the solids, we have a T1 or a proton density image. Look at this scan. CSF is dark. The grey matter is darker, greyer than the white matter. This is a typical T1 weighted image. In B, CSF is still dark, even though its signal intensity is slightly higher than in the T1 weighted image. Contrast between the grey and white matter is reversed. This is a proton or spin density weighted image. And as grey matter has a higher water content, in other words, contains more protons, its signal intensity is higher than that of the white matter. In C, CSF has a higher signal intensity than grey and white matter. The image is T2 weighted. These are rules of thumb only. Actually, to be really sure, you'd have to look at two images taken with different imaging parameters. Why? Look at this figure. You can see that in this example, the T2 curves start at different heights and cross each other. They do not have to run parallel, as depicted in the previous illustration, which was only done for didactic reasons as it is easier to understand at the beginning. the fact that the curves intersect is very important. With a TE before the crossing point, TE1, tissue A will have a higher signal intensity. With a TE right at that point, TEC, we cannot distinguish the tissues at all, as they have the same signal intensity. Thus, you might be unlucky and choose a pulse sequence with just those imaging parameters that do not allow tissue differentiation, which is the reason for performing two different examinations with different T1 and T2 weightings. With a TE beyond the crossing point, TE2, tissue A will have a lower signal than tissue B. Before this crossing point, which you do not know looking at an image normally, the relative signal intensities are still governed by differences in T1. The tissue with the shorter T1, or the higher proton density if we have a long TR, still has the higher signal intensity. Only with longer TEs does the T2 weighting come up. Think about that for a moment. Now, we've already heard about many parameters that influence the MR image. T1, T2, proton density, pulse sequences, TR, and TE. But there are more. For example, contrast media and flow. The fact that flow influences the MR signal has been known for a long time. The first experiments on this subject were carried out more than 40 years ago. Interestingly, this phenomenon was used to measure flow in the fuel pipes of satellite rockets, without having to put any obstruction into the flow lines.
3, 2, 1, 0.
The subject of how flow influences the MR signal is rather complex and difficult, but let us at least get some idea about it. In this figure, we have a body section through which a vessel is crossing. When we send in our first 90-degree pulse, all the protons in the cross-section are influenced by the radio wave. After we turn the RF pulse off, we listen into the section and record a signal. At this time, all the original blood in our vessel may have left the slice being examined. So there is no signal coming out of the vessel. It appears black in the image. This phenomenon is called flow-void phenomenon. This is not the only way in which flow may influence the image. There may be all kinds of things. For example, flow-related enhancement. This illustration shows a blood vessel going through a slice which is being examined. The figure represents the situation before the 90-degree pulse. Immediately after the pulse, longitudinal magnetization is tilted 90 degrees. If we wait some more time before we send in a second 90-degree pulse, protons will have undergone some relaxation. And there is some longitudinal magnetization again, as shown by the arrows pointing back up. The protons in the blood vessel, however, have left the slice and been replaced by protons that still have all of their longitudinal magnetization. If we send in a second 90-degree pulse now, there will be more signal coming from the vessel than from its surroundings, because there is more longitudinal magnetization at this time. The whole subject with signal strength and flow effects is actually much more complicated. For example, when you do multi-slice imaging, in other words, taking images of more than one slice at the same time, we'll hear about this technique later, Now, flow imaging, in other words, taking images of more than one slice at the same time, we'll hear about this technique later. The signal also depends on the direction of the flow. In addition, it differs over the cross-section of a vessel, depending on the flow profile and whether there is laminar or turbulent flow. If you want to know more about this, you should look it up in one of the comprehensive standard textbooks. They will also give you more information on MRI angiography. In this technique, the fact that flow influences the MRI signal is used positively by displaying the moving protons. Certain so-called paramagnetic substances have small local magnetic fields which cause a shortening of the relaxation times of the surrounding protons. This effect is named proton relaxation enhancement. The body contains paramagnetic substances under normal circumstances. Examples are degradation products of hemoglobin, for example, deoxyglobin and methemoglobin, which are found in hematomas, or also molecular oxygen. Gadolinium, a paramagnetic substance, is used as an MR contrast medium, marketed as Magnavist. Chemically, the substance is a rare earth. As gadolinium is toxic in its free state, it is bound to DTPA in a certain way called chelation, which solves the problem of toxicity. The pharmacological properties of gadolinium DTPA are very similar to the ones of contrast media in conventional radiology. Gadolinium DTPA, however, is even better tolerated. The contrast medium has an effect on both the signal intensity of T1 and T2. They shorten the T1 and the T2 of their surroundings, meaning that the respective curves are shifted towards the left. In effect, for a certain TR, there is more signal. For a certain TE, there is less signal. In this figure, the signal intensity for two tissues, A and B, is illustrated. The IV-administered gadolinium DTPA enters tissue A, but not tissue B. The T1 of tissue A becomes shorter, and the T1 curve is shifted to the left. The result is that the signal from tissue A at time TR is stronger than it was before, and the two tissues can be better differentiated because there is better contrast. What happens when we perform a T2 weighted examination after contrast medium application? These are the T2 curves of tissue A and B. As we have just heard, the contrast medium shortens T2 of tissue A, which is entered by the contrast medium, shifting the T2 curve to the left. Now, there is less signal coming from tissue A. Loss of signal is often more difficult to appreciate than a signal enhancement, as we have just seen. This is why T1 weighted images are the predominant imaging technique used after contrast medium injection. As the substance is not distributed evenly throughout the body, Now, certain so-called paramagnetic substances have weighted more difficult to appreciate than a signal enhancement, as we have just seen. Will also be influenced differently. As the substance is not distributed evenly throughout the body, signals from different tissues will also be influenced differently. Vascularized tumor tissues are enhanced, for example. It is also important that the gadolinium does not go through the intact, but rather the disrupted blood-brain barrier. It has been shown that the use of contrast media improved lesion detection and diagnostic accuracy of MRI. It may, for example, help with differentiation between tumor tissue and surrounding edema, which might be otherwise indistinguishable. Gadolinium DTPA entering into the tumor tissue shortens the T1, thus making the tumor bright in a T1 weighted image, while the surrounding edema may not be influenced at all. There is another beneficial effect caused by contrast media. As we've already seen, gadolinium certain so-called There is another beneficial effect caused by contrast media. As we've already seen, gadolinium DTPA shortens T1. Thus, we are able to shorten TR in our examination. And because imaging time depends on TR, as we will see later, imaging then may take less time. Ready for a review? As we know by now, many parameters influence the appearance of tissues in an MR image. For example, T1, T2, proton density, pulse sequence. With a short TR, we get a T1 weighted image. With long TE, the image is T2 weighted. Flow effects can be variable and cover the spectrum from signal loss to signal enhancement. Paramagnetic substances, for example the contrast medium gadolinium DTPA, shorten T1 and T2 of the surrounding protons. This results in a signal increase in T1 weighted images and a signal decrease in T2 weighted images. T1 weighted imaging is the preferred technique after contrast medium injection.